So last time, well, today we'll talk more about ext. And so these are functors, ext, and extensions. And this will explain why it's called ext. So last time we computed we defined functors xi. So x was fixed, and then there's some variable. So we define these functors by resolving the target variable by taking an injective resolution of the target applying the Hom functor to that resolution to form a complex, and taking cohomology of the resulting complex. And that's fine as a definition. You can use it to prove all the good formal properties of ext. It is not generally useful for calculating these things because injective resolutions tend to be very huge. So for instance, in abelian groups, the standard injective model out of which you build other ones is cube mod z. And if you're studying maps into that, they can get very, very large. So it's important to be able to compute x via some other resolution. And so this is called balancing ext. We have balancing Tor where we could resolve either variable. Here, we're going to show that we could have computed this instead of resolving the target variable. We can resolve the source variable by a projective resolution. So this is our basic proposition. So proposition, this is called balancing ext. And it says the following. So suppose P dot to x is a projective resolution of some module. And y to I dot is an injective resolution. Then there are three things we could do. We could look at the Hom complex from P dot to I dot, or from x to I dot, or from P dot to y. So then the claim is that we have quasi-isomorphisms as follows. So in the center, we have the Hom complex from P dot to I dot. And if I Hom P dot into y, and then compose with the map from y to I dot, I'll get a map of complexes. And the claim is that's a quasi-isomorphism. And similarly here. So this will be the Hom complex from x, thought of as a complex in degree 0, to I dot. And these maps are just given by the composite. So these maps given by composite with the, no, augmentation or co-augmentation of the resolutions. Okay. And the proof of this is going to be somewhat similar to the proof of balancing of Tor. If you remember, to compute the tensor complex, you write down a double complex involving all the individual tensor products, and then you take tote sum of this. And we showed that if you look at the rows in one direction and take the kernel, you get one complex. If you take kernels of the column, you get the other complex. And then we got a quasi-isomorphism of tote of the kernels with tote of the double complex. And that depended upon knowing that if I had a certain kind of double complex with either exact rows or exact columns, then tote plus of that was acyclic. So it'll be something similar here, except for tote product. So proof. So let's write down the relevant double complex for this. So let's recall how the Hom complex looks. So recall the differential in the Hom complex. So if I have a map of some degree between complexes, so I don't know, suppose this is m dot to n dot of some degree. Then D in the Hom complex of F, that's supposed to produce a new map whose cohomological degree is 1 greater or whose homological degree is 1 less. And then I could ask, well, if I evaluate it on an element, what should it do? And it's set up so that applying the Hom complex across the tensor is a map of complexes. So this ends up being the following. Let's see, I think it's F of D of X minus 1 to the degree of F D of F of X. So that's how the differential works. And then you can see where that comes from a double complex as follows. And I'll make the double complex already with squares anti-commuting rather than commuting, so that when I just sum along diagonals, I'll get a differential. Okay. So then consider the double complex with anti-commuting rows, anti-commuting squares. So it looks as follows. So I'm going to have Hom from P0 into I0. And then I can compose with the map in the differential in I and continue like that. And also, I can consider Hom from P1 into I0 and do the same thing. And so the vertical maps are given by composing with the differential in P. and so on. And this sign, where does it appear? It appears on d of something in the target. The target is, in our case, I. So this looks like it will be di. This thing is of degree 0. This one is of degree 1. So this will be di. This one would be of degree 1 or minus 1. So it's minus a minus. So this is the plus. And so on. Okay? And these just involve dp. There's no sign there on the dp. Okay, so that's a double complex, except with the squares commuting. And note, note a few things about it. First, if I take tote product, tote product gives us exactly this Hom complex. And that's the thing about which we're trying to prove something. Second, because P0 or P1 or so on is projective, if I augment this to put in here Hom P1 into y, Hom P0 into y, and so on. Or up here, Hom x into I0, Hom x into I1, and so on. So I want to note that the rows of this augmented double complex these will be exact because I'm homming something projective into an exact sequence, which is y, I0, I1, and so on. These are exact since the PI are projective. And likewise, the columns of the other augmented double complex these are exact since we're homming into something injective. Okay. And now we're going to prove a little lemma, which says if I have some double complex like this with exact rows, then tote product is 0, is acyclic, has no cohomology. Or similarly, if I have a double complex like this with exact columns, the tote product will be acyclic. So how does that help? So we make the third observation that we made when we balanced Tor. So up to a shift, the cone of either of these maps, so this one in the middle is tote product of the central double complex. If instead I took tote product of this augmented double complex up to a shift, I would be getting the cone of the left-hand map. So up to a shift, the cone of this map is the tote product of the double complex augmented on the left maybe I should say extended. Augmented usually means map 2. So the rows of maybe the extended double complex. Extended on the left. The cone of this is tote product of the double complex set on the left, and likewise for cone of the other one. Hom complex from P dot to I dot, receiving a map from Hom complex from X into I dot. So I could take the cone of that and up to a shift, that will be the tote product of this extended double complex where I've extended on the top. So you check that the same way we did for the tensor product. And now it remains to check exactness of these cones. Okay. So these maps will be quasi-isomorphisms precisely when the cones are acyclic. So the desired maps, the given maps, precisely when these cones are acyclic. And so we need a criterion for checking that. Okay? And this will follow just from a very general fact. So this follows from the following lemma. So last time we had something called the acyclic assembly lemma, which was about how to tell when tote plus was acyclic. Here this will be the tote product version. So this is again the second part of the acyclic assembly lemma. Okay, so it says the following. Suppose we have a double complex of the form. So let me just draw it. So my convention has been to draw left to right and top to bottom. You need some convention. So it's going to be a double complex like this. It goes off maybe to infinity in going down, but all up here, it's 0. Okay, so it's kind of bounded above in this convention. So it's a double complex of that shape, but with exact rows. Then tote product is acyclic. So note this applies to, in our case, that would apply to the double complex, which is extended to the left. Everything above it is 0. And likewise, just by rotation. So this is equivalently by rotation. Sort of, I don't know, rotation reflection. Just, I don't know, put it in a mirror and stand on your head, and then it's the same statement. So equivalently by rotation reflection, if given a double complex like this, where it's all 0 to the left with exact columns. Then the tope product is acyclic. Okay, so let's indicate the proof. Note that this does imply what we want, because the hypotheses apply to these extended double complexes. We're actually proving more than we need. Okay, and the proof is very similar to last time. So we start with a cycle. In this tope product, we just write down explicitly what it means for it to be a cycle. We'll get a bunch of relations involving differentials and elements. And then we'll see inductively that we can make it exact if it's a cycle. So every cycle is exact, therefore there's no homology. Okay, so proof. So up to translation, I mean, I can kind of fix the origin wherever I want. So I can declare this to be 0, 0. So up to translation, we may assume our double complex, I would say it's enough to show every 0 cycle in tote product of, let's suppose it looks like this. I have x0, 0, x0 minus 1, x0, 1, and its 0 is all up here. This is, I guess, first row, 0th column, first row minus first column, first row, first column, and so on, like this. Okay. So we want to show every 0 cycle, and every 0 cycle is coming from something along this diagonal, is exact. Okay. So let's just write it out. Let's suppose that I have a 0 cycle, and let's suppose I've already fixed the signs so that the squares anticommute.